the epochs. Okay, entropy coding, inverse entropy coding, which covers information theory, VLC, Huffman arithmetic. We have a little bit left. Okay, so we're gonna finish up this guy, and then we move on to quantization. Okay, and if we have some time, we're gonna start going into the prediction, transformation, decorrelation part. Okay, then we're gonna connect everything together. Hopefully, it will make sense. Okay. So that's the goal. Now, before, let's do a quick review. So where were we? We were at arithmetic coding. Okay? And I want to revisit this example really, really quick. Okay? This is adaptive arithmetic coding. This is how state-of-the-art entropy coding is right now being implemented in practice. This exact algorithm is what being used in practice now. So, and as you can see, it's very adaptive, right? We did not make any assumptions on the behavior of the symbols or anything like that. Automatically, we keep track of the frequency, the occurring frequency of the symbols. And let the arithmetic code figure itself out. Okay. So as you can see, in the beginning, since we don't know any information about A, B, and C, the sensible thing to do would be assume that they are equally likely, right? So 1/3 for A, 1/3 for B, 1/3 for C, and that's how we get this assignment. And instead of putting 0.33, 0.66 here, I put 33%, 66%. Because I'll need those percentage later on, okay? You can go back and figure out exactly the numbers that you are supposed to put here, okay? Later on. Now, and if you receive B, then you update your table, okay? And since now, with this current state table, B is twice more likely to happen comparing to A or C. So likewise, it will get allocated a longer length. Okay, so that's how the allocation in the second step is quite different from the allocation from the first. And as you can see, B now has a much larger interval. Okay, so then you can figure out what is the lower bound of the interval, the upper bound of the interval, so on and so forth. The next guy you receive is C, so you will update the table, and then you do the allocation accordingly. Okay, so this guy get 2/5, this guy get another 2/5, this guy get only 1/5. Okay, that's how I get 0, 20%, and then 40% here, and another 40% there. So as you can see, the more you let this algorithm run, the more it will converge to the true occurring frequency of the symbols. Okay, but it demonstrates a very important properties of arithmetic coding, which is the size of the interval is roughly the product of all the probabilities of occurring of the symbols that you observe. The size of the interval, okay, is roughly the same as the product of all the probabilities of occurring of the symbols. Okay, that is very important because from here we can see that each symbol's of probability P of X contributes log base 2 of P of Xi to the output. See, with much larger intervals, we have the freedom to pick a nice binary number to transmit to the other side. So we don't need to spend a lot of bits to describe. But when the interval getting smaller and smaller and smaller and smaller, you need a lot of resolution for the final number to send over, right? And that's where you have to spend a lot of bits. Okay, so arithmetic coding, if you take a look at this from this very hand-waving viewpoint, actually approaches entropy if you let it run for a long time. Okay, so it's this arithmetic code can be proven to be near optimal. Okay, with even with finite precision arithmetic, okay, because a whole number of bits or bytes must be sent to the other side. Okay, we rarely send. Usually we round it off to bytes, and then we send it to the other side. We don't send like 2 bits, okay, or 2.5 bits, right? So that's why it's not exactly optimal, because of practical implementations. And then there are other implementation issues which we don't have time to talk about. But in practice, you probably prefer integer implementations. You don't want to multiply by things like 0.3333. Okay, it's very difficult to represent such a number in using the computer, right? We want nice integers number, for example, and then we would like something to have incremental output, right? You don't want to wait until everything happens and then start sending the numbers over. Okay, you start sending bits over along the way when you encode. Okay, so in practice, we never wait until the end of the symbol string to send a number over. Okay, we start sending these number over. We start sending these bits over along the way when we go along with the coding scheme. Okay, so I'll let you figure that problem out. Okay, another thing with arithmetic coding is that this scheme is very sensible is extremely sensitive to error. Right? If our communication channel has error, we're in big time trouble. Suppose that this bit, instead of being 1 and it's turned to 0, all bets are off, right? There's nothing we can do. Unicode if this guy becomes 0, okay, it gets flipped to 0. Everything behind is basically garbage. You just have to throw them away. Okay, so it needs a lot of resynchronization. So basically, after you let it run for a while, you stop and then you start fresh. Okay, so that's create a synchronization point so that if you make a mistake here, at least you only have to throw away this much of information, not the entire string from now until the end of time, right? So those are practical issues that we have to that distinguish the toy example that we have versus the way arithmetic coding is implemented in practice. Okay? Now, today let's finish up run length coding. And the main idea is this, okay? We will try to encode long runs of a single symbol by the length of the run. Okay? Now, so this is also a lossless coding scheme, and this is our first attempt at inter-symbol coding. Inter-symbol means you actually take a look at your neighbor and try to make a decision, okay? Up until this point, even with arithmetic coding, we never take a look at the neighbor, right? The only thing we know about the neighbor, the only thing that allows us to go on is the frequency bit, right? How many times something happens, right? But we never care about our neighbor. Agree? Okay, so here, this is our first effort at trying to do something that involves the neighbor, right? Suppose that you have a long runs of 0. Okay, 0, 0, 0, 0, 0, 0, 0. Okay, it would be pointless to encode 0, then encode another 0, encode another 0, encode another 0, right? Especially if we know that is very based on An Jones and Min's lectures. We know that when we design good transform, we're going to try to have as many 0 coefficients as possible, right? The entire idea about having a good transform is being able to approximate something with only a few non-zero coefficients, correct? Everything else should be 0, right? So we're going to encounter a situation where we have a long string of 0. And if you have to encode a long string of 0, one guys after another, you're going to run out of bit rates very, very quickly, right? So let's try doing this thing. And it's best to illustrate by an example. This is actually a block that I copied out from the JPEG coder. Okay? As you can see, let's count, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 symbols here, 14 zeros here, another ones here, that's 13 plus 14 plus 37, and you come up with 64. So that's a typical 8 by 8 block. Okay? A typical 8 by 8 block that you just yank out of JPEG. And it's typically, with a good transform, with a good quantizer, we're going to see something like this. Okay? So you see strings of zeros, right? 2 0 here, 1 0 here, 1, 2, 3, 4, 5 zeros here, 14 0 here, 37 zeros there. And we're going to try to take those long runs away. Okay? So this is how JPEG recommends doing this. Okay? You encode, you transmit